All right, let's jump straight in. We're looking at a fascinating paper today called Mind Captioning, Evolving Descriptive Text of Mental Content from Human Brain Activity.
Yeah, this one's a big step.
So if you just need the quick takeaway, the really short version.
Okay. Basically, this paper introduces mind captioning. It's a new way to decode brain activity, specifically fMRI, and get actual descriptive text out.
And not just like single words.
No, that's the key.
Yeah.
It handles complex visual stuff, things happening, relationships between objects, and turns it into structured sentences.
How does it work in a nutshell?
It's a two-stage process. First, they use a linear decoder to get semantic features, think using vectors, from the fMRI data. They use large for those features.
Okay, linear decoding.
Right. Then stage 2 is this clever iterative thing using a masked language model, large, to actually generate the text. It keeps refining the sentence until its semantic features match the ones decoded from the brain.
And the big findings?
Well, two huge things. One, it genuinely captures the relational structure, the grammar, the meaning, not just a bag of words. Two, it works for both seeing something and just remembering it.
Wow. Perception and imagery.
Exactly. And maybe the most surprising part, it did all this pretty well, even without relying on the brain's main language areas.
Which opens up possibilities for, say, brain-computer interfaces for people who can't speak, right? Like with aphasia.
Precisely. It's a potential pathway for decoding nonverbal thought directly into text.
Okay, let's dig into that technical side, because decoding complex stuff like relationships, that's been the real hurdle, hasn't it?
Oh, absolutely. For years, fMRI decoding was pretty good at identifying, is this person looking at a face or a house? Or maybe pulling out a single noun.
Static things.
Static things, exactly. But trying to get something like the dog chased the frisbee, that was really, really tough. Capturing that semantic structure was the bottleneck.
So why was it so hard? What were the old methods missing?
Well, earlier approaches kind of fell into two camps, and both had issues. First, you had database search methods.
Right, where you decode some brain features and then search a big library of sentences for the best match.
Exactly. You decode maybe some high-level concepts, dog, park, running, and then find a sentence in your database like, a dog is running in the park.
What's the problem there? Seems reasonable.
The big limitation is your output is completely restricted to whatever sentences are already in your database. It can't generate anything truly novel or capture nuances not already written down. Very limited diversity.
Okay, restricts creativity. What was the other approach?
The other way, especially with powerful models coming online, was to try and use complex nonlinear models, think deep learning, to map brain activity directly to text, like training a big AI captioning model on fMRI data.
Like a GPT or maybe a vision language model like GIT, but fed brain scans instead of images.
Kind of, yeah. And those models can produce really fluent, grammatically correct sentences. They sound great.
There's always a but.
The but is huge here. Interpretability and fidelity. How do you know the sentence reflects what's actually represented in the brain versus the model just, using its incredibly strong language knowledge to fill in the gaps plausibly?
So the model might just be making a really good guess based on a few decoded concepts, imposing its own structure.
Precisely. It might generate the dog chased the frisbee, because that's a common scenario. Even if the brain data only weakly represented dog and frisbee, you risk introducing spurious information structure that wasn't explicitly there in the neural signal.
That's a critical point for neuroscience. You need to trust the output reflects the brain, not just the model.
Exactly. Fidelity is paramount.
So mind captioning was designed to get around these problems, aiming for both interpretability and fidelity. Let's break down their two-stage solution. How does stage 1, the decoding part, ensure that fidelity?
Okay, stage 1 is mapping the fMRI activity to semantic features. The crucial design choice here was to use a linear model, specifically L2 regularized linear regression.
Okay, hold on. Linear. In the age of deep learning everything, why go simple and linear? Seems almost backwards.
It seems simple, but it's deliberate. Linearity forces a direct proportional mapping. If a semantic concept isn't explicitly linearly represented in the pattern of voxel activity, the model can't just invent it or find some complex roundabout connection.
So it's like using a straight ruler. It only finds direct connections.
Pretty much. It ensures they're probing explicit representations in the brain. They're not letting a complex model potentially hallucinate meaning. And the target space for this mapping, features from large, a powerful language model good at capturing nuanced meaning.
Okay, so stage one gives you this high-dimensional semantic fingerprint derived linearly from the brain activity. Reliable, but it's not text yet. How does stage two generate the actual sentence?
Right. Stage 2 is where the generation happens, and it avoids that database limitation we talked about. They use another pre-trained language model, Roberta Large, but specifically as a masked language model, NLM,
MLM like Bert.
where it fills in missing words. Exactly. The process starts with basically nothing, just a placeholder token like UNC. Then, iteratively, it uses Roberta to propose words or refine the sentence.
Okay, but wait. Now I have the same skepticism as before. Roberta is incredibly good at language.
Yep.
Isn't it just going to generate a fluent sentence based on its internal knowledge, maybe nudged by the brain features? How do we know Roberta isn't adding that spurious structure?
That's the absolute key question they had to address. And the answer lies in how Roberta is guided. It's not just generating freely, it's an optimization process driven entirely by feature alignment.
Feature alignment. Explain that.
Think of it like this. The linear decoder gives Roberta the target semantic fingerprint from the brain. Roberta generates a candidate sentence. Then, critically, they calculate the Roberta semantic features for that candidate sentence.
Ah, okay.
And the system's goal is to minimize the difference, the distance, between the candidate sentence's features and the target features decoded from the brain.
So it's not optimizing for, does the sentence sound good? It's optimizing for, does the meaning vector of this sentence match the meaning vector we got from the brain?
Precisely. It forces the generated text semantic content to stay tightly tethered to the linearly decoded brain representation. Roberta provides the linguistic building blocks, but the brain-decoded features dictate the final structure and meaning.
That makes a lot more sense. It's a clever way to leverage the power of LMs without letting them run wild. Linear decoding for fidelity, then feature-guided generation.
Exactly. It sidesteps the database limits and the nonlinear interpretability problem.
Okay, let's talk results. When they applied this to people watching videos, the perceptual content, what did the output look like?
It was pretty remarkable to see the examples in the paper. The process would start with garbage text, maybe just the UNC token, and then iteratively refine itself. You'd see fragments appear, then slowly coalesce into coherent, descriptive sentences that accurately match the video content. Things like a person throwing a baseball, or describing specific actions.
And quantitatively, did it work well?
Oh yeah, the numbers were strong. They used a whole battery of standard metrics, BLOU, Meteor, Rouge, Cider, BERT score, comparing the generated captions to human-written ground truth captions for the videos.
These are common in machine translation and image captioning, right?
Correct. And across all these metrics, the discriminability was significantly high. That means the system was very good at scoring the correct caption, much higher than incorrect ones for a given brain activity pattern.
And the practical test, identifying the video.
They did a video identification task. Given the brain activity, could the system pick the correct video out of a set of 100 possibilities? Chances 1%, obviously. They were getting close to 50% accuracy.
Whoa, okay, nearly 50% accuracy on picking one video out of 100 just from brain scans. That's impressive.
It really is. It shows that decoded information is highly specific.
But still, that nagging question about structure, did they really decode the sentence structure or just a really good list of keywords that Roberta stitched together grammatically? This leads to the shuffling test, right?
Yes, the shuffling test was crucial. This was designed explicitly to prove that the word order, the syntax, the relational information like subject, verb, object, was genuinely coming from the brain data, not just imposed by Roberta's language priors.
How did it work?
They took the captions that the system generated accurately. Then they deliberately scrambled the word order. In one version, they shuffled all the words randomly. In another, they just shuffled the nouns.
Okay, breaking the sentence structure.
Exactly. Then they reevaluated how well these shuffled captions matched the original brain-decoded features.
And the hypothesis is, if the brain-encoded structure, the original order should match much better.
Precisely.
Yeah.
And that's exactly what they found. When the words were shuffled, the match score, the discriminability, dropped significantly. The system's ability to identify the correct video also plummeted.
So messing up the word order broke the connection to the brain data.
Yes. It proved that the original word order wasn't accidental or just a byproduct of the language model. The specific sequence of words, the grammatical structure, was being actively guided and constrained by the information decoded from the brain. The coherence was real.
That's compelling evidence. Okay, if the brain is encoding this structured semantic information, where is it doing it? This gets us to the neural basis and that surprise about the language network.
Right. Usually, if you talk about structured thought, especially related to language, you immediately think of the classic language areas in the brain. Broca's area, Wernicke's area, that whole frontotemporal network.
Makes sense. That's where language lives, neurologically speaking.
And their initial analyses, called encoding analyses, seem to support this. They compared how well different brain areas predicted the semantic features from DeBerta versus purely visual features from a model called Timesformer. The semantic features were better predicted in both the higher visual cortex, HVC, and that classic frontotemporal language network. So yes, the language network seemed involved in processing these semantic features.
Okay, as expected. But then came the ablation test.
This is where it gets really interesting. Ablation means computationally removing or ignoring a brain region to see if it's necessary for a task.
Yeah.
They asked, what happens if we run the whole mind captioning decoding process without using any data from the voxels in the language network?
So just ignoring that entire classical language system.
Completely ignoring it. And the result?
Let me guess. Performance tanked.
Nope. That's the shocker. Performance was barely affected. They could still achieve almost 50% video identification accuracy out of 100 choices, even with the entire language network excluded from the decoding.
Wow. Okay, unpack that. What does that mean?
It strongly suggests that while the language network might process this kind of information, it's not strictly necessary for generating these structured descriptions from visual input, at least via this method. The core structured semantic information seems to be represented elsewhere.
So we can potentially separate the neural basis of structured nonverbal thought from the mechanisms of language production itself.
That's a major implication, yes. It supports the idea that the rich, structured understanding of a scene doesn't have to be encoded within the language system. It suggests this information is more distributed.
Where then, if not the language network?
The results point towards a broad network extending from more anterior parts of the visual cortex up into parietal and frontal regions, but critically, outside the canonical language areas.
Did they get any more specific about how this distributed representation might work?
They did propose a potential gradient based on their encoding results. They suggested that maybe the more posterior parts of this network handle isolated concepts like recognizing dog or person. But the more anterior regions, still outside the language network, might be where these concepts get integrated into a structured, contextual representation, person walking dog.
Interesting, like a hierarchy of integration happening before it even needs to become language.
Kind of, yeah. An integration of visual semantics that precedes linguistic formulation.
Okay, this whole idea of decoding nonverbal structure naturally leads to the next big question. Can it decode internal thought? Like mental imagery or memory. That's the focus of the last part, the cognitive bridge.
Exactly. The ultimate goal for many BMI applications isn't just decoding what someone is seeing, but what they're thinking or remembering. So they tested this directly.
Oh.
They took the decoders that were trained only on brain activity recorded while subjects were watching the videos. Perception. Then they applied these same decoders to fMRI data recorded while the subjects were asked to simply recall those videos from memory. Pure mental imagery.
Using a perception-trained model to decode memory, that's a tough generalization test. Did it work?
Remarkably well, actually. For subjects who were good at the recall task, the system could identify which of the 100 videos they were recalling with nearly 40% accuracy.
40%, just based on recalling. That's really significant.
It really is.
Yeah.
It shows that the way the brain represents the semantic content of actually seeing something and just imagining or remembering it shares a significant underlying code, at least at the level these DeBerta features are capturing.
So those semantic features act like a common language, a bridge between perception and imagery.
That's precisely what they argue, and they tested it further. They compared how well different types of features generalized across perception and imagery. They looked at purely visual features from Timesformer, visual semantic features from sleep, and these semantic features from DeBerta.
And the DeBerta semantic features were the best bridge.
By far. They showed the highest generalizability. The performance drop when moving from decoding perception to decoding imagery was smallest for the semantic features. It suggests these features capture a more abstract, core meaning representation that's shared between seeing and remembering.
That's powerful, and they even got results from single trials.
Yes, which is important for potential real-world use. They showed they could get comprehensible descriptions even from a single instance of mental imagery recall, which hints at applications for fleeting mental events, maybe even things like dreams, though that's still speculative.
Yeah, and the language aspect. You mentioned native Japanese speakers.
Right. The system generated fluent English descriptions even when decoding brain activity from native Japanese speakers who were thinking about the video content.
So it's truly decoding the underlying non-linguistic concept and translating that into English.
It certainly seems that way. It's translating the brain's semantic representation, which appears to be independent of the person's native spoken language, into the target language of the system, which was English. Decoding thought, not language.
Okay, let's try to wrap this up. The mind captioning method seems like a really innovative step forward. It's like an interpretive interface for our nonverbal thoughts.
I think that's a good way to put it. It cleverly uses linear decoding for fidelity, and then this feature-guided iterative generation with large language models to get structured text out, balancing interpretability and performance. It really pushes past the limitations of older methods.
But no paper is perfect. What are the limitations or next steps?
They acknowledge one key limitation themselves. They use natural videos. While that's realistic, it means the scenes often follow typical patterns. Dogs chase balls, people throw things. It doesn't rigorously test if the system could decode truly atypical structures, like a man bites a dog.
Because it might just default to the common dog bites man structure.
Potentially. So future work really needs to use controlled, maybe even nonsensical stimuli to push the boundaries and see how well the structural decoding truly generalizes to unusual relationships.
Makes sense. Test the edge cases. And finally, this success. Decoding structured thought, even from single imagery trials. It brings us right up against some pretty significant ethical considerations, doesn't it?
Oh, absolutely. We have to talk about this. The closer we get to reliably decoding internal mental content, especially nonverbal, perhaps even preconscious or primitive thought, the more urgent the ethical discussion becomes.
Mental privacy is the obvious one.
Mental privacy is paramount. The potential for misuse, for accessing thoughts someone hasn't chosen to express. It's profound. We need robust frameworks.
What does that look like?
It means moving beyond just basic informed consent. We need regulations ensuring explicit, ongoing, and fine-grained consent regarding exactly what kinds of mental content can be decoded and when. Subject autonomy has to be the absolute priority before any kind of widespread application of these brain-detection technologies is even considered. The potential benefits are huge, especially for communication disorders, but the ethical guardrails need to be built now, not later.